Hello everyone, welcome to Vedantu JEE English. I am Diksha, your chemistry master teacher. So everybody do let me know in the chat box if I am clearly visible and audible to all of you. Yes everybody, hi Abhinav, Sahaya, Rama, Dhanush. How are you all students? So today we are going to do hyperconjugation and aromaticity, right? See, we have done inductive effect, resonance we have seen. Now these two effects will do, right? After this, stability of intermediates, that is the next lecture that I am going to take in the next class, that is tomorrow. To understand that, you should be able to understand all these effects individually, right? Then stability of intermediates, acidity and basicity will be answered based on these effects, and based on GOC directly the questions are asked in the exam. When I say directly, that means directly you can see 3 to 4 questions just based on GOC, right? And not only this I am talking about the direct questions. Indirect questions are also asked, that is asked in terms, for example, some reaction is given to you and they will mix GOC into it and they will ask you a question, and it's very easy to get number out of this because predictable questions are asked, right? So let's see everybody. Firstly, before moving forwards, I hope so that you all have registered yourself into MVSAT program. The registration is completely free of cost, right? If I would have been at your place, right, why would you not give this test? First is it's free of cost, registration is free. Second is you're already preparing for JEE or JEE Advanced, right? And basic level of questions will be asked in MVSAT scholarship program. And I genuinely feel if you're attending my lectures, right, you will be able to crack it, right? You will be able to crack it. And if you get into 2.5 lakh students, yeah, that is a big amount, right? That is a big chunk. You will get 100% scholarship on all Vedantu courses, offline, online. And guys, you will also get 150 crores of scholarship, worth of scholarship, 2 crore worth of cash prizes and rewards like iPhone, iPads, drones, all these things you will get, right? So what else you need, right? One-on-one mentorship regarding your whether you are a dropper or you're in class 11th or 12th, that will also be provided. AI related things will be also be provided to you, right? So all these things, you just need to register yourself 4th, 5th, 11th and 12th of October. You have the offline test dates, right? And which center you can visit your nearest Vedantu center, right? Yes, okay. Thank you so much, LM, thank you so much. Hi, Shiv, CK Gaming, hello. Yes, so now let's talk about this, guys. This is the last homework that I gave you. And how many of you do your homework? Very rare students, right? So let's see how many of you have done the homework. I genuinely expect very less students to do the homework because you guys disappoint me a lot, right? Today also I'll give you one question for homework, right? You will do that. Promise me that in the chat box that yes ma'am, we'll do our homework, right? Let me see in the last class in resonance how many of you have done the homework. See, watching the lecture is one thing and applying that in your homework is another thing, right? Okay, so I'll just see. Yes, so very good. Rajesh has done the homework. And Deepan has done the homework. Very good Deepan, very good Rajesh. Other students have not done the homework. So guys, start doing it, okay? You will also feel happy, right? You will feel motivated. When you're able to solve the questions, you will feel happy about it, right? Okay, so the question is the stability you need to tell, right? As I told you in the last class that the neutral ones are maximum stable, so it will be third. Then you will see pi bonds. Pi bonds are same in both of this. This is one pi bond. But here negative charges on oxygen, here positive charges on oxygen. So negative charge on electronegative is more stable. So it will be 2, then it will be 1. So answer will be 3, 2, 1, which applies for C. So answer will be C is the correct answer here. Easy peasy question, right? And that's your JEE Means 2024 question. I try to give you that question which is the PYQ, so that when you solve it, you know that you are solving a PYQ and you're also solving a homework, right? Okay, that will motivate you only. Now let's start with hyperconjugation. Let's understand that, guys. Hyperconjugation. In last time we discussed about resonance effect. So everybody do let me know in the chat box what was resonance. Resonance was delocalization of pi electrons, right? Here it is delocalization of sigma electrons, right? It is delocalization of sigma electrons, right? In resonance, what we were doing, this was the thing. For example, this is the thing, right? Just taking one example out of that, we were moving these pi electrons and you were able to form this kind of resonance. So this is sigma, this is pi. So we are moving the pi electrons, right? When you have a double bond, always pi electrons will break first, right? Now, ma'am, what is this delocalization of sigma electrons, right? We'll talk about, because next 45 minutes is totally going to be your hyperconjugation effect, right? So we'll talk about how it is done. Just remember that this is sigma electrons. We are not talking about pi electrons here. Other names for this one is no bond resonance, Annulenes effect or Bacon-Nathan effect. These two effects already name that is based on the scientists. So this will see that why it is called as no bond resonance. It is a kind of resonance which is no bond because delocalization is there. To understand that, we'll have to draw the structures, why the name are so. So to understand the structure, you will have to understand what actually shows hyperconjugation effect. What is the condition that I'll say this structure will show hyperconjugation effect? So simple conditions are related to alpha carbon and alpha hydrogen. For that, you should know what is the alpha carbon, what is the alpha hydrogen. So whatever is the mean, let's say I'm talking about, I'm looking for hyperconjugation in carbocation, right? Then the carbon that is next to it is alpha. The carbon that is next to alpha carbon will be beta, right? And the hydrogen that is attached to alpha carbon is alpha hydrogen, right? So the condition is that alpha carbon should be sp3 hybridized. This carbon should be sp3 hybridized. There should be at least one alpha carbon that is sp3 hybridized, right? sp3 hybridization means sigma plus lone pair has to be 4. If sigma plus lone pair, this I have told you in chemical bonding also, when the hybridization will be sp3, when the sigma electrons, sigma bonds plus lone pair is equals to 4, then we are going to say it is sp3 hybridized, right? And if it is sp3 hybridized, it should have at least one alpha hydrogen, only then hyperconjugation is possible. Otherwise, hyperconjugation will not be possible, okay? That is the condition, right? So now, I'll give you 2-3 structures. You need to tell me whether hyperconjugation will be possible or not. Just tell me yes or no, whether it will be possible or it will not be possible. I am not asking you to make hyperconjugating structure. Tell me how many hyperconjugating, no. Just tell me hyperconjugation possible or not. Based on 2 factors, alpha carbon sp3, alpha carbon should have at least one alpha hydrogen. That's it. These 2 conditions and answer me. So here if you see, this is the carbocation, this is the main thing, this is the main part that we are focusing on. This will be alpha, this will be alpha. Now this alpha carbon has, this is connected to one hydrogen, right? This is sigma, this is sigma, this is sigma. Okay, so I'll just draw it like this. You can also draw it like this, right? This hydrogen is actually nothing but this hydrogen is placed over here. So what I'll do, just give me a second, what I'll do here, right? This will be hydrogen here. Okay. Now, 1, 2, 3. 3 sigma, here also 1, 2, 3 sigma. That means, can I say this is sp2 hybridized? This is also sp2 hybridized, right? So that means definitely no hyperconjugation. No hyperconjugation. So you need to see where hyperconjugation is there or not. Hyperconjugation, yes. Okay, not possible. Here it is sp2. Now here if you see, this is the main part that you have. This is alpha, this is alpha, this is alpha. This carbon is connected to 3 hydrogen and 1 carbon, so that means it is sp3. Okay. This is connected to 3 carbon and 1 hydrogen, so that means it is also sp3. This is also sp3. So it will show hyperconjugation. You will say hyperconjugation is definitely possible. Okay, because you have sp3 hybridized carbon atom, alpha carbon is at least 1 you need to have. You have 3. So this will also show hyperconjugation. This set will also show. This will also show. They have alpha hydrogen also. You need only 1 alpha carbon, and to that alpha carbon, which is sp3 hybridized, at least 1 hydrogen will be attached, right? Then you will say that hyperconjugation is possible, right? If you see this here, this is alpha, this is the mean, this is alpha, this is alpha, this is alpha, right? If you see, this carbon is connected to 4, this carbon is connected to 4, this carbon is connected to 4. So all are sp3 hybridized only. But tell me, is any of them has 1 alpha hydrogen also? Do they have alpha hydrogen? This is beta carbon. This hydrogen connected to this carbon is beta hydrogen. You need alpha hydrogen. You don't even have a single alpha hydrogen here. This does not contain hydrogen. This does not contain hydrogen. This does not contain hydrogen. So that means no hyperconjugation is possible here. No hyperconjugation is possible in this case. Why? Not because it's sp2 or sp3, it is sp3 carbon, but no alpha hydrogen is present here. That's why it is not going to show hyperconjugation. That is clear. 2 conditions of hyperconjugation. Now, ma'am, why you have these conditions? Okay, we'll talk about the structures, right, one by one. Firstly, carbocation, then carbanion, alkene, free radical. These we are going to talk about. Ready, everybody, to draw the structures with me? Slightly, it will be, if you're doing this for the first time, this may get like slightly on the difficult part, right? But if you understand it like calmly and you have patience, right, definitely it will become easy, right? But full focus has to be here, right? Yes, everybody. How to know alpha hydrogen, Anjali? See, carbon, alpha carbon, this one, the hydrogen connected to the alpha carbon is alpha hydrogen, right? So here to this carbon, you don't have any alpha hydrogen. Alpha hydrogen means the hydrogen connected to alpha carbon, right? You don't have any hydrogen connected to this. No hydrogen, no hydrogen. This hydrogen, this hydrogen, these are connected to beta carbon, not alpha carbon, right? Okay? Yes? No, I am fine, I am fine. Is it heavy? Is my voice like echoing? Okay. Now, next part is to draw these structures, right? Let's draw. Let's draw these structures, students. Firstly, I'll take the example of carbocation. Now, carbocation means you have a positive charge here. Let's say this is H, right? This is C, this is H, this is H, and this is H, right? Firstly, we need to understand what kind of transfer is happening here. So what exactly will happen here? I'll just draw the orbital diagram of this one. See, this simply means that here for this carbon you will have a bond here, and for this carbon also you will have a bond, that is making a sigma bond here. They are making a sigma bond, right? Here this is making a bond with hydrogen, this is also making a bond with one more hydrogen, one more hydrogen, right? This is from hydrogen, hydrogen, hydrogen. This we have done enough in chemical bonding, right? So why I am telling you this? So that you understand things in a better way. I don't want you to cram, okay? So this I am just telling you that this is the structure. Here this sigma bond I have drawn, this sigma bond I have drawn, this sigma bond I have drawn, this sigma bond I have drawn. Further you will have this and this sigma bond, or you know what I will do here, because it's sp2 hybridized. If you see, this carbon is sp2, it has only 3 bonds, so this is sp2 hybridized, okay? So here you will have sp2 hybridized means it will be trigonal planar, so that's why like a trigonal planar I have marked it. And here you have hydrogen, here you have hydrogen, where I am filling the electrons, right? Firstly tell me, is that clear that how come they have these kind of electrons here, right? Is that clear to everybody? What kind of structure we are making here, right? What kind of structure we are making here? Now this carbocation means this is a empty p orbital of carbon which is not undergoing any hybridization. So this I have told you multiple times that carbon is 1s2, 2s2, 2p2. So its orbital excited state diagram will be, if this is 2s, this is 2p, this is going to be 1, 2, 3, 4. Right? Wait a minute. And if you take one carbon, one electron from there, this one is your unhybridized p orbital, which is empty. Empty p orbital. This is making sp2 hybridization. This is making sp2 hybridization. That's why this is sp3, sp2 hybrid orbital. This one is empty because from that carbon which had 6 electrons firstly, you are taking out 1 electron, right? So that's why it will be empty, right? Earlier it was like this. Earlier it was like this. When you take out electron, make it a carbocation, that means it is losing the electron, right? So it will become like this. Now students, tell me one thing. Now students, tell me one thing. Can you see here what kind of bonding, what kind of transfer will happen here? So what will happen? Sigma electrons are going to move. This particular 2 electrons, right, will shift here. These 2 electrons will shift here. That means the shifting is from sigma to empty p orbital. P orbital shifting. So the shifting is from sigma to empty p orbital, right? Empty p orbital is there. This is sigma, this is empty p orbital. This kind of sigma electron shifting is happening here, right? Let's see how to draw the structures now, right? If you have, let's say, this is C, this is H, this is H, this is H, this is C, this is H, this is H, okay? Now this is your carbocation. So what exactly is going to happen here? This particular bond, the sigma bond will shift here, right? When the sigma bond is shifting here, what will happen? This is C, this is H, this is H. This will form a double bond because the sigma bond is shifting here. This carbon, this hydrogen, this hydrogen. Now this carbon tetravalency is completed. So the positive charge is not going to be on carbon, rather it is going to be on hydrogen, right? And it's not like this is an ion and this will leave this space, no. They are actually, this H positive is actually in the vicinity of this compound. That is no bond resonance. Why it was called no bond resonance? Because the sigma bond will break and it will become a double bond. And this, can you see between this H positive and this whole compound, there is resonance, but there is no bond here. That is a very beautiful thing, right? So, ma'am, can this bond shift here? Ma'am, can this hydrogen show the similar thing? Yes. It can also do the same thing. This is H, let's say this is H, this is H. Let's say this hydrogen, this bond is shifted here. Then you will have this kind of hyperconjugating structure. Let's say this particular hydrogen, right? This is breaking its sigma bond, double bond you have here, this is H, and here you will have H positive, and these are your hyperconjugating structures. Okay, so can I say one thing here? This is the mean carbon, right, and this is your alpha carbon. Each alpha hydrogen, here this alpha hydrogen, here this alpha hydrogen, here this alpha hydrogen. Each alpha hydrogen is corresponding to a different hyperconjugating structures. That is why what we had, right, if this would be sp3 only, then the electrons will shift here. That is the first reason. Second is why we need alpha hydrogen. Because if there is no alpha hydrogen, then hyperconjugation is not possible only. So at least one alpha hydrogen was required because of that. So now in the exam, right, for the exam point of view, right, this I just told you so that you understand that why it is called no bond resonance and everything, right. This you should know. Sometimes they can, till now they have not asked that kind of question. Till now they just ask the application of hyperconjugation. But what if they ask you which of the following is not a hyperconjugating structure? Even then you can answer, right? So that means full hyperconjugation you have done, right? Now, what is the application of knowing this thing? What is the application of hyperconjugating structures? Let's see. It says that number of alpha hydrogen, more the number of alpha hydrogens you have, more will be the hyperconjugating structure. More the hyperconjugating structure, more is going to be the stability. And in inductive also we were talking about stability. Resonance also we check the stability. Here also we are checking the stability, right? So you have more the alpha hydrogens, more the hyperconjugating structure. The number of alpha hydrogens is equals to hyperconjugating structure. Like here you have 3 alpha hydrogens, so it is giving you 3 hyperconjugating structure. This is not a hyperconjugating structure. This is the first hyperconjugating structure, this is the second one, and this is the third one. So number of alpha hydrogen is representing the hyperconjugating structure. More the hyperconjugating structure, more will be the stability of that particular carbocation, right? Okay. No. It's actually not like it is existing as a charge, okay, right? It's not like they're existing as a charge, right? They are in conjugation with each other, right? That is hyperconjugation. Sometimes it is existing like this, sometimes like this, sometimes like this, sometimes like this, right? Don't take it as an ion. This H positive is not an ion, it is in the vicinity. It will sometimes gain the, it will sometimes have the sigma bond, sometimes this will not have, sometimes this will not have. Right? So it's not like it will go away as an ion, right? That will not happen here. Now guys, I'm going to give you some questions, right? And you need to tell me which is more stable, which is less stable. So let's see the application part of it. Rama Raju will not do that here, okay? Catenation is for a different topic, okay? That is not related to this one. Okay. So you need to tell me, just calculate the alpha hydrogens, right? And more the alpha hydrogen, more will be the stability, right? You just need to tell that. So if you see this here, this is carbon, this is CCH3, CH3 and CH3, and this is positive. So I can see this is alpha, this is alpha, this is alpha. So total you have 3, 3, 6, 3, 9. So you have 9 alpha hydrogen. That means 9 hyperconjugating structures you have, right? Here, this is the mean, so this is alpha, this is alpha, this is having 1 hydrogen, 1 hydrogen. So we can say total 2 alpha hydrogen, that means 2 hyperconjugating structures you have here, right? 2 hyperconjugating structures you have, and if you see which one is more stable, this one or this one, more the hyperconjugating structure, more will be the stability. So A is more stable as compared to B. So answer will be A is more stable as compared to B. Second question you can see on your screen is, this is A, this is B and this is C. calculate the alpha hydrogens here, and that will tell you which is going to be most stable. Yes, Sai, I will definitely provide you with that. Okay, so now let's see this here. This is the mean carbon, this is alpha, this is alpha. This is the mean carbon, this is alpha, this is alpha. This is the mean carbon, this is alpha, this is alpha. So here this one is sp3, this one is also sp3, this one is 1, 2, this is sp2, a double bond you have here. A double bond you have, this will be sp2. You have a double bond, this will be sp2. You have no double bond, sp3, right? Because hydrogens we are not writing here, right? Here you have, by blue I am mentioning the hydrogens, okay? So here you will have 2 hydrogens, here you will have 2 hydrogens, here you will have 2 hydrogens because to complete the tetravalency. Here you will have 1 more hydrogen, either way you don't need it, right? Why? Because this is sp2, this is the will not show only. So here, no hyperconjugating structure. Why? Because there is no alpha carbon which is sp3. Here you will have 1, 2, 3, 4. So 4 alpha, or you can just write 4 hyperconjugating structure. In this case, you have 2 alpha hydrogens, so 2 hyperconjugating structures, and you can answer it like this, that E is the maximum, then you have C, then you have B, and ACB is going to be the correct answer here. Is that clear to everybody or not? Right? ACB, very good, Rama Raju, very good, right? Let's see this here, let's see this here. This is A, this is B, this is C, and this is D. And this is D. Let me know in the chat box if you can answer the hyperconjugating structures here. Let's see if you can answer that. This one is alpha, this is alpha, this is alpha. This is here, this one will be alpha, that is connected to it. Here this is alpha, this is alpha, and here you have this as alpha, that's it. So guys, if you see this here, this is sp2. So it is not going to show any hyperconjugation because it is sp2. Alpha carbon is not sp3. Alpha carbon should be sp3. If it is not sp3, not even one alpha carbon, you'll say, ma'am, but this is sp3, this is sp3. I just want alpha carbon which is sp3. So this is the only alpha carbon that I have, and that is sp2. Here this is sp2. So this will be cancelled, like this is cancelled, but this is sp3. Here this is sp3. Here all of them are sp3. Okay. Now let's talk about the hydrogens. Here you have to complete the tetravalency. You need 3 more hydrogens. I am mentioning red with hydrogen, right? Here you need 1 more hydrogen. Here you need 3 hydrogens here. 2 hydrogens here, 2 hydrogens here. So it will be 3, 4, 5, 6, 7. 7 hyperconjugating structure. This is 1 hyperconjugating structure, and this is 3 hyperconjugating structure. So you can say more the hyperconjugating structure E is greater, then you have C, then you have B, then you have D, and ACBD is the correct answer here. Yes, everybody, do let me know. CABD, CA, no, ACBD. ACBD, because this is carbocation, so that will be alpha, this will be alpha, this will be alpha. You also need to complete the tetravalency of that carbon. According to that, you will see what is the number of hydrogens, alpha hydrogens. Okay, yes. Okay, now next is, let's talk about free radical, right? What is a free radical? Everybody in the chat box, what is a free radical? What do you mean by a free radical? What do you mean by a free radical? A free radical is, here you have C, this is H, this is H. In place of carbocation, you should have one free radical here. That means only one electron it is having. So if I want to draw the orbital diagram here, it will be actually something like this. Here you will have a sigma bond that is there. Here you have sigma bond, here also sigma bond, here also sigma bond with the hydrogens. Yes, here also one sigma bond with the hydrogens. That will be there. And here you will have a p orbital which is half filled, right? So if you see, this is 1, 2, this is sigma, this is sigma, this is sigma, this is sigma, this is sigma. Okay, so we know that what will happen here, this bond will shift here. That means in reality, this is shifting here, right? In reality, this is shifting here. That means the shifting is from sigma to half filled p orbital. P orbital. Sigma to half filled p orbital. This kind of shifting is happening. Okay. This is not vacant. This is half filled. In carbocation, you have vacant. In free radical, that is half filled. Okay, done? Yes, everybody, do let me know, is that clear? How it is half filled, how it is sigma, right? Okay, how it is a sigma. Sigma, this is sigma, sigma 2, this one is your half filled, right? It's not vacant. Right now, when you want to draw the resonating, hyperconjugating structures here, right, how you draw it. So let's see. CH, it is same as carbocation, right? It is same as carbocation. So what you will have, this is H, this is H. This is already one electron here. Homolytic cleavage, that means here you will have one electron here and one electron will go here. Homolytic cleavage will take place. You will have C, this is H, this is H. Now one free radical from this carbon, one free radical already here will make a double bond. This is H, this is H, and here with this H you will have one free radical that has shifted with homolytic cleavage, right? Similarly, you will have, if this hydrogen is doing homolytic cleavage, then you will have one this H here, one this, double bond CH. Similarly, this hydrogen also, right, this is carbon, this is hydrogen, this will be H free radical, double bond CH. Similar case that we did there. Okay, similar case, this is first, this is second and this is third, right? Okay, time, repeat please. What should I repeat? Tell me. Okay, so is that clear everybody? Now shall we do the questions of free radical hyperconjugation in the same way we did questions of carbocation hyperconjugation? It is same it is, not even a single difference, right? Same way like you used to see carbocation as main carbon, here you will see free radical as main carbon. So this is the main carbon, this is alpha, this is alpha. The carbon that are next to it is alpha, right? This is the main carbon, this is alpha, this is alpha. This is the main carbon, this is alpha, this is alpha, right? This is the main carbon, this is alpha and this is alpha, okay? Now let's see which is sp3 and which is sp2, according to that we'll see, right? Yes, okay? So this alpha, if you see, this will be one hydrogen also here, so this is sp3. To complete the tetravalency, you don't need any hydrogen. This is also sp3, right? This is sp2, so it will, hyperconjugation will not take place. This also require one more hydrogen. This is sp2, sp3. Okay, this is sp2, so it will not do any hyperconjugation, but this is sp3, right? Here it is sp3, and here you will have one more hydrogen. Here you will have 3 hydrogens, and this is sp3, right? Just tell me the number of hyperconjugating structures that you have, right? Negative charge hyperconjugation, Abhishek, that we'll talk about later on. After free radical, we are going to do alkene, and after that I'll talk about carbanion. Okay, so if you see this here, this is having no alpha hydrogen, so no alpha hydrogen also means no hyperconjugation. Again cross, this is one hydrogen, so one hyperconjugating structure, right? This is going to have one hyperconjugating structure because of this hydrogen. This is going to have one hyperconjugating structure because of this hydrogen here, right? Wait a minute, this will show 2 hyperconjugating structure. I forgot this one. One only it will show. Oof, yes, one only it will show. All are saying 1, 1, 1, 1, is it? This is also showing one hyperconjugating structure. This is also one hyperconjugating structure. This is also showing one hyperconjugating structure. This one will be most stable because it is showing 3, 4 hyperconjugating structure. So this one will be most stable. Now you will say, ma'am, but ma'am, how do I answer the order here? This is A, this is B, this is C. If hyperconjugating structures are same, then there are other factors that we'll see, right? Okay. So based on hyperconjugating structure, you can't differentiate this, right? So you can only tell the most stable out of this, right? That is 4th one, right? Okay. Next is alkene. So alkene is, this is the main group that you have. This is carbon, this is CH. Okay. Now its diagram is quite complicated, so let's just directly remember this sigma, right? What will happen here? This bond will shift here, this bond will shift here, right? So that means you are adding these electrons, shifting sigma electrons to the anti-bonding pi orbital, right? You are shifting this to sigma 2. This is a very important question in itself. Directly also they can ask you this in theory points, that in alkene from sigma to bonding or anti-bonding it is shifted. Bonding is not free, anti-bonding it is shifted, right? That means pi star. Sigma to pi star. Okay? Sigma to pi star. Right? Okay, everybody. Yes, let's see how to draw the structure. Is also similar only, right? Structure is also same. I'll just tell you how to draw the structure, right? Same thing we'll do here. Same thing. This is C double bond. This is C, right? Let's say this is H. This is H2. So what will happen? This bond will shift here, this will shift here. You will have C, this is H, this is H. Here it will be H positive because the bond, sigma bond has shifted. This will be double bond, this is C, this is CH2 negative, right? Overall it is neutral, positive, negative, right? It was also neutral. Similarly, this bond can break, this hydrogen can break the bond. So similarly, you can have CH, H positive, C double bond, CH2 negative. Similarly, this hydrogen can also break its bond and you can have H positive, C double bond, rest of it will remain the same, right? That is this one. So these are the 3 hyperconjugating structures, 1, 2, 3. Can you see it also depends upon the number of alpha hydrogens that you have? Yes, everybody. Can you see this also depends upon the number of alpha hydrogen that you have? Yes, everyone. So tell me one thing. Same way, we are just like we did questions for carbocation. Similarly, we'll do questions for alkene. Same kind of questions, okay? Let's see. This I have already told you that it is accepted in anti-bonding pi orbital, right? Okay, so this is A, this is B and this is C. You need to tell me which one will be most stable, okay? Which one will have more number of hyperconjugating structures, that means more number of alpha hydrogens, okay? Yes, everybody. So this is the mean, this is the mean. You can't say this is alpha, this is alpha. Both are mean. Just like carbocation was mean, just like free radical was mean, similarly this C double bond is mean, right? Next to it you will have alpha, this is alpha, this is alpha. Next to it you will have alpha, this is alpha, this is alpha. Next to it you will have alpha, this is alpha, this is alpha. Double bond, the carbon next to it will be alpha, right? Now you need to also complete the structure here. It is C, so it will be CH3, right? This will also be CH3, right? This is also sp3, this is also sp3. 4 bonds it is making, so it will be 6 hyperconjugating structures, right? This one, if you see, this is alpha, this is sp3, which is connected to 2 more hydrogens to complete its tetravalency. So that means it is, wait a minute, this is connected to 3 more hydrogens to complete its tetravalency. So this will have 2, this is 5 hyperconjugating structures, right? Okay. Now let's see. Now in these kind of structure, hydrogen is never written here, right? So this is the carbon. Now no double bond is there, that means it is sp3. To complete 4 bonds, to complete tetravalency, 1 hydrogen will be connected here. Similarly here it is sp3. How come? Why? Because no double bond is there, right? And here it will be 1 hydrogen to complete the tetravalency, right? So it will have 2 hyperconjugating structures. So we can say this is A is maximum, then you will have C, then you will have B. So answer will be A is having maximum number of hyperconjugating structure, right? Okay. Okay, yes. Done? Done everyone? Done, done, done? Let's see this one. Let's see this one. This is alkene, this is alkene. Next carbon connected to it is alpha, alpha. Next carbon connected to it is alpha, 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 alpha. Right? Here no double bond to this one. That means it is sp3. This has 2 to complete the tetravalency. 2 hydrogen is required. To complete tetravalency, 2 hydrogen is required. Here to complete tetravalency, 1, 2 hydrogen is required. 2 hydrogen is required. Here 3 hydrogen is required. Here 3 hydrogen is required, because in these kind of structures hydrogen are not mentioned, right? This is 4 hyperconjugating structures. This is 2, 2, this is 3, 6, 7, 8, 9, 10 hyperconjugating structures. So definitely B is more stable as compared to A. So answer will be B greater than A, right? Yes, definitely Sri Ram, the syllabus is exactly the same, right? You can definitely watch it, right? Okay, it will be beneficial for you, right? Okay, tell me, any problem here? Any problem in this, like calculation of alpha hydrogen, calculation of alpha carbon, hyperconjugating, so if any problem in that, ma'am, why hydrogen is required? It is not, it's not like it is, the structure is actually not like this. This is C double bond, this is CH It's just that we write it this way. This will be CH2, this is CH2, this is CH2, this is CH2, this is CH2. This is, yes. Actually, the structure is like this now. We just don't write hydrogens in these structures, right? Okay? We just don't write these structures like that. Understood? Actually, this and this structure is same. We don't write hydrogens here, right? So that's why for the ways tetravalency should be completed. Carbon should always form 4 bonds. When you see that there is only 2 bond carbon is forming, extra 2 hydrogens you will attach. But see, that should not be connected to double bond there. Okay? Concept is that, students, concept is, if carbon and carbon you have, this situation you have, right? That means this is carbon, this is carbon. So 3 hydrogens should be connected to each of them. If you have this chain, that means this is C double bond. Double bond means only 2 more required you have. Okay? If it is triple bond, that means only 1 more required you have. Got it? So that's how it is done. That is the reason I am attaching hydrogen in every case. Okay, now let's see this one. Let's see this one, everybody. Let's see who will answer me that. I hope so, Durga, that is clear to you now. So this is the mean. This is the mean. I just firstly circle what is the mean. Okay, this is the mean. Now let's write alpha. This connection is alpha. This directly connected. Direct connection is alpha always. Direct connection is alpha. Direct connection is alpha. Direct connection is alpha. Right? Direct connection is alpha, direct connection is alpha, direct connection is alpha, right? That is the alpha carbons. Okay, yes. Now, this will not be sp3. Why? Because no double bond is there. Now, to complete 4 bonds, I'll add 2 hydrogens. To complete 4 bonds, I'll have to add 1 hydrogen. To complete 4 bonds, I'll have to draw 3 hydrogens. To complete tetravalency, I'll have to complete, I have to draw 2 bonds here, 2 bonds here. This is also sp3 only, right? So this is H, this is H, this is H. This is H, this is H, and here this will be H. Now tell me all the sp3 carbons tetravalency is completed, right? Now, 1, 2, 3, 3 hyperconjugating structure. 1, 2, 3, 4, 5, 6, 7, 7 hyperconjugating structures, and here you have 3, 4, 5, 6 hyperconjugating structures. So answer will be B, answer will be B, then you have Ca, B, then C, then you have A, and I can see very good Bhuvnesh, very good Rama, very good, awesome. Very good. Awesome, awesome, awesome. Yes. Very good, Tarun. Good going, good going. So, let's see next question here. This is A, B, C and D. Let's see if you can answer this or not. Let's see if you can answer this or not. This is the mean. Alpha is 1, 2, 4 are directly connected, 3 are directly connected, 2 are directly connected, no directly connected there, right? So here, each of them, by red I am now drawing by blue I will draw the hydrogen. So this is 1, 2, 3 hydrogens, 3 hydrogens, 3 hydrogens, 3 hydrogens. Here also 3, 3, 3. Here also 3, 3, okay, that's it. So, this is 12 hyperconjugating structure, this is 3, 3, 9 hyperconjugating structure, this is 6 hyperconjugating structure, this is no hyperconjugating structure. So, answer will be A, B, C, D is the correct answer. Can I see that? A, B, C, D. Very good, Durga, Bhuvnesh, very good. Very good, Tarun, very good, awesome, awesome, awesome. Okay, great. Vadi, what you can do is, I'm about to complete this topic, so I would advise you right now just focus on what I am telling you. After this, you can re-watch the session, right? And I'm going to start aromatic compounds maybe in 10 minutes. So that is a fresh topic, right? So you will get clarity there, right? So wait for aromaticity and start from there. And this you can watch the replay of this one. Now this one is very important, right? This one is very, very, very important. Mark it. Important. This one is very important, very high probability. So this is mean, this is mean, this is mean, right? This is alpha, this is alpha, this is alpha, okay? Here you have three hydrogens here, 3 hydrogens here, 3 hydrogens here, 3 hydrogens here, 6 alpha hydrogen, that means 6 hyperconjugating structures, 6 hyperconjugating structures, 6 hyperconjugating structure. Now ma'am, why, like how we should answer which one is more stable, right? Now how we should answer, okay? Got the question why this is so important? All are same ma'am? Yes, all are same, right? Chalo, let's see how we will answer this, right? First thing is, let's see that we are clear on that based on hyperconjugating structure, directly we can't answer this, okay? So I'll just show you how to answer this, right? Firstly, tell me out of this, is there any geometrical isomer? Those who have no idea about GI, right? Just tell me about cis and trans. Okay, geometrical isomer is when you have this, I'll talk about in isomerization. Don't worry about that. When we'll do isomerization, we'll do like multiple questions based on that, right? So don't worry about that. Right now, just see this thing. If to a double bond, this is the situation. GI will only exist if 1 is not equal to 2 and 3 is not equals to 4. This I have told only for those students who have actually done isomerism sometime in their life. If you have never done that, it's okay. We'll do that, right? So I'm just erasing this for those new students who have no idea about that, right? Now, if you know geometrical isomerism, then you know that when same group, this is hydrogen, this is hydrogen, this is CH3, this is CH3. This is CH3, this line means methyl. When you have nothing, that means hydrogen. That I have told you. This is like the base of organic. When you have just one line, that means they are talking about CH3. When nothing is drawn, that means hydrogen to complete the tetravalency of this carbon, right? Okay. Now see one thing. Here 2 hydrogens are like next to each other. That means this will be cis, right? And this is opposite. That means this is going to be trans, right? In trans, less repulsions are there. Right? Less repulsions are there. In cis, this is big methyl group, this is big methyl group, repulsions will be more, right? So that means here you have more repulsions. More repulsions means less stability. So I can confirm here that B is definitely more stable than C. Right now we have just done B is more stable than C. We have no idea about A. We'll do that, right? Understanding A is even tough, right? So understanding A is the main part, but just now see B is more stable than C. Now I don't know, A can be here, A can be here. No idea. Let's see and get that idea, right? Where you should have A, here or here. B and C is clear, right? B and C is clear, right? Okay. B because bulky group on opposite sides. Yes, B is more stable. Right, now let's talk about A. For A, what I'll do, I'll draw the hyperconjugating structures. Okay. I have to come here because see, the comparison of A is with trans. Whether A is more stable than trans or less stable. Right, so I'll compare these two structures. Here you have C double bond C and here you have one hydrogen. This is one CH3. So how you can draw it? This is CH3 and here you can do CH3 here also. Right? Okay. Isn't it? Now I need to see the alpha for hyperconjugating structure. This is the mean. So this will be alpha or this will be alpha. So I'll open any of the alpha here. So I'm opening this alpha here so that I can draw the hyperconjugating structure of that. Right? Now this is alpha. How hyperconjugating structures are done, everybody? It is that this bond is going to, any bond, this bond may shift here or this bond may shift here or this bond may shift here, any bond will shift. So I'm shifting this bond here, right? This bond is shifting, this bond will, why I have drawn one line here, I don't know. Wait a minute, let me just clear that. Yes, okay. So now here, this bond is shifting here, this bond will shift here. I am just drawing one hyperconjugating structure just to explain you. This is H, this is H, this will be negative single bond, this is CH3, this is double bond, this is CH2 and this will be H positive here. Tell me, is that thing clear to everybody how I have drawn this hyperconjugating structure? If you have any problem like how I have drawn this, then do let me know what I have done. This is alpha. From the alpha hydrogen and carbon, the bond will break and shift here, right? Then this bond that already is a double bond will shift here. You will have a negative, you will have a double bond here, right? Okay. Yes, everybody. Yes, everybody. Let me know. I don't know why people want to get blocked. Okay. Now, let me know in the chat box, guys, if that is clear, right? Now, I'll do the same for trans. This is C double bond C. This will be, I am not even doing trans. I am just normally saying this is CH. Okay. You know, let's make it like this. This is C. Let's make it this CH3. Cis or trans, if I don't mention the stoichiometry, cis and trans will be like this. You have cis or trans, it will be like this now, right? Majorly I have drawn here trans, whatever you can draw. I just, hyperconjugating structure will be same for both of them. It's just that in trans repulsions are less, that's why it is more stable, right? So if you see this here, in this case also same, this is alpha. So this alpha is going to, I'll just mention here, this is alpha. Same, this alpha, this bond is going to break, it will shift here, this bond will shift here. And let's draw this. This is C, this is CH3, this is H, this is negative here, right? This is C, this is H, this is double bond, this is CH2 and this is positive here. Tell me, is that clear how I have drawn these two structures? Now see, based on inductive effect, how I will answer this, right? Okay. Okay, everybody. Ma'am, how do you find alpha? It's alpha carbon. Durga, this is the mean and the carbon next to it is alpha. This is also alpha, this is also alpha. Like here, this is the mean, this is also alpha, this is also alpha. I have chosen one of them. Even if you draw with this one, it will be the same. Even if you draw with this one, it will be the same, right? Tell me if you have any problem till here. Any problem in drawing these hyperconjugating structures? Right, because these hyperconjugating structures are going to tell you which is more stable, right? See, now here, can you see this is the negative charge, right? And here, inductive effect by the plus I effect of this CH3, you are providing the electrons to a anion. So whenever you have a carbanion and you provide the electron, it will become unstable. Here you don't have as such thing. Here you don't have any CH directly attached. CH is there, but it is not directly attached, right? So that is why this was A now, this was A and this was B, right? That is why A is more stable than B, and we have already discussed that B is more stable than C. Okay, understood how the answer is A, B, C? Yes, right side is less stable due to plus I. Yes, hence the answer is not B, C, A. Why are you saying you're telling the right approach but you're answering it wrong? Because of plus I, this is less stable, right? So A will be more stable, na? A, B, C it will be, isn't it? Yes, everybody, isn't it? A, B, C, right? Okay, everybody clear? Now let's see this, let's talk about this one. This is A and this is B, and if you have to tell me what is the correct answer here, tell me about it, right? This is mean, this is mean, this is connected, directly connected is alpha, directly connected is alpha, directly connected is alpha, directly connected is alpha, okay? Direct connection is only one, that is alpha, right? So, no double bond in alpha carbon, can you see? So, to complete the tetravalency, 2 hydrogen, 2 hydrogen, 2 hydrogen, 2 hydrogen. Here we need 1 hydrogen. So, it will do 8 hyperconjugating structure. Here you will have 1 hyperconjugating structure. So, definitely A is more stable as compared to B. Okay? Okay, yes everybody. Definitely A is more stable. Ma'am, say his name or he won't leave. I am also very stubborn. Those who are like, ma'am, say my name, I never say their name, right? You need to answer something if you want to, like, you know, ma'am, please say my name, please say my name. I don't know what will happen. What is this obsession, huh? What is this obsession? Chalo. Now let's see carbanion, okay? Let's talk about carbanion, everybody. Ready for that? Ready for that? Yes. So, carbanion, it actually does not show any hyperconjugation, right? Let's see how. So, this sigma, this sigma, this sigma, this sigma, this is fully. Now, do you remember when we talked about a carbocation, this was empty. This was empty when we talked about carbocation. That's why the transfer was happening. When we talked about a free radical, this was half filled, that's why the transfer was there. Now it is already fully filled. So why will it show any hyperconjugation? If someone is already very rich, you will not give them money. You will not see someone already in Mercedes and you will say, hi, hello, take this 100 rupees note from me. You will not do that. You will see someone who is not able to eat anything, right? They are just lying there on a road, right? They are hungry. You will give them rupees. You will give them money. You will give them food because they are poor, right? So the poor person you will give the money, na? Rich person you will not give money, right? So that's why here you have no hyperconjugation, right? Okay. But Definition of hyperconjugation is basically the transfer, the delocalization of sigma bond. Sigma bond is shifting, right? Sigma bond will shift only if something is poor, only then it will shift, right? So if there was no electrons, then sigma bond will shift. If you have only one electron, then sigma bond will shift. But if you have two electrons, sigma bond will not shift, right? Sigma bond will be like, why will I shift? He is fully happy, he has full electrons, why will I shift and give the electrons? So no hyperconjugation in carbanion, okay? That is clear, everybody, why there is no hyperconjugation in carbanion, okay? There is also a specific case where it shows, right? But before that, tell me in general, do you understand why there is no hyperconjugation? Now let's say, here it will show. If in a carbanion, this is actually C, Cl, 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 CH2 negative. If in a carbanion, the alpha carbon is connected with so many electron negative atoms, then it will show hyperconjugation. Let's see how, right? Now this is the electronegative, so it will take away the electron, it will take away the electron, it will take away the electron. See this very carefully. It will take the electron, it will take the electron, it will take the electron. So the electron is pulled, pulled and pulled like this. Can you see? It is not, it is pulling. That means this carbon is becoming electron deficient. This carbon is actually now the poor person. Now this carbon is a poor person. Earlier, if you talk about this thing, CH3, CH2 positive, this carbon was the poor person. Now this carbon is the poor person. That means opposite hyperconjugation will take place. That means this negative charge will shift here, right? How? See this, right? This negative charge will shift here, right? And the Cl, who is already crazy, he is like, I'll take electrons from you, I'll take electrons from you, he will go, right? Okay, so what you will have C, Cl, Cl, this will be Cl negative, this will be double bond CH2. This kind of hyperconjugation will be there. Tell me guys, is that clear? This kind of hyperconjugation will be there. Now like just we have drawn this one, I'll just also draw it on the next page. See, if you have CH2 negative, CCl, Cl, Cl, because of its electronegative nature, this electron will shift here and this will go. So you can have C, this Cl, this Cl, this is Cl negative because it has bent. This is CH2. Now if this Cl is going, so it will be C, Cl, Cl, Cl negative, CH2. If this Cl, then it will be Cl, Cl, Cl negative, double bond CH2. Now this hyperconjugation is called as minus H. Earlier, all the hyperconjugations that we have done is plus H, right? Because what we were doing, if you see in all the other hyperconjugation, I'll just show you the case of carbocation. If you see this carbocation was actually the electron deficient. This was donating, that is plus H. This is plus H, right? This was donating, right? If you see in free radical also, the carbon free radical is actually accepting. That means this one is donating. Again, it is plus H, right? If you see in alkene as well, right? In alkene as well, this is accepting the electron. So this is again plus H, right? In simple carbanion, so definitely it's not showing anything, but When electronegative element is attached, it is showing you minus H here. Because now the carbon ion is not accepting, it is donating, right? Okay, that is reverse of, that is minus hyperconjugation, right? Definitely. If you answer Jayana, then definitely, right? Yes. Got it? Understood? Tell me if you have any problem here. Any problem here? In carbon ion, it should be not anion, it should be anion, A, right? So in carbon ion, this is the thing. Now let's see if you can answer this hyperconjugating structure for this compound. Let's see. In the end, last two questions, then we are going to start with the aromaticity, aromatic, non-aromatic, anti-aromatic, most important topic, right? Yes. So now if you see this here, this is the mean, because every electrons is being, you know, delocalized in the benzene ring. So that is the mean. This will become alpha, 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 this will become alpha. Hydrogens you have to see, this will have one more hydrogen, this will have one more hydrogen, two more hydrogens, this will have no more hydrogen, two more hydrogen. So you can see 1, 2, 3, 4, 5, 6. 6 hyperconjugating structure here, right? Okay, 6 hyperconjugating structure here you have. Yes. Got it, everybody? There is no such time for all these stupidities, right? Some kids are here, na, I have like felt some kids are here not to study. It's just time pass they are doing. They are wasting, you know, my time also, your time also they will waste. Like seriously. So these kind of distractions definitely we have on YouTube, right? So that's why I always tell the students in batch you don't have these kind of distractions. There I don't have to block anyone, right? I know what is this obsession, right? What are these things that you are doing, right? That is not going to take you anywhere, right? So now what about this one? Here if you choose carbocation as mean, then this is alpha. It is sp2. So that will have no hyperconjugating structure. So I'll choose this one, right? Benzene. This is alpha, this is alpha. This alpha is sp2, so we'll not do that. This is sp3, which has 2 more hydrogens here. So it will be 2 hyperconjugating structures, right? Okay, everybody, let me know if that is clear. Now we are going to start with aromaticity, and I'm waiting for your chats in the chat section. If you have any problem in what we have done till now, then do let me know in the chat box so that we can start with. Achha, firstly we have to do electromeric effect also. So very simple effect, right? Electromeric, very hardly 2 minutes it will take. See, what is electromeric effect? When you have, it is firstly a temporary effect. That means when you have a double bond, right? In the presence of some reagent, when the reaction happens, then we tell whether electromeric effect has happened or not, whether it's plus C or minus C. So how do you define that? See, like you have this particular carbonyl compound, and let's say you have H positive here as a reagent, right? If H positive you have here, right, we know that this is partially positive, this is partially negative, here also it's partially positive, this is partially negative. That we are sure about, right? Now see one thing, Because of partial negativity, this is more electronegative, electrons will jump here. Because now this will become O negative. So this H positive is going to attack here. So when the shifting of electron and the attack of reagent is on the same atom, that is plus E. Shifting of electrons, attacking of reagent on same atom, that is called plus E, right? Let's say you have Cn negative. Here we know that these electrons will shift here because it is more electronegative. But then it will become CO negative, this is positive, and this will shift here. That means Cn negative is going to attack here. Shifting of electron, attacking of reagent is on the adjacent atoms, right? That means on different atoms, that means this is minus of E. Okay. Wait a minute, is it written class 11? Oh, wait a minute. I'll just change that, okay? I'll just change that. This is for actually both 11th and 12th, right? But majorly this is in 11th. Okay? Okay, wait a minute. See, done? Right? I have corrected it. Okay, chalo, let's see. Right? Okay? Yes. Now let's talk about aromaticity. Everybody ready for aromaticity? It's a most important thing, right? Most important, right? Okay? Yes. Okay, chalo. Now let's talk about aromaticity, right? So in aromaticity, we'll define aromatic compounds, non-aromatic compounds, anti-aromatic compounds. There are so many factors that you need to understand here, right? So firstly, we'll understand the conditions, which will show even where we have to see, right, whether aromaticity is there or not. So the first condition that you have is that compound itself, in all the compounds, should be planar. That means all the atoms should be sp2 hybridized, which are connected, right? Complete conjugation should be there. Conjugation is what, like double, single, double, or you can have double, single, negative charge. This kind of complete conjugation should be there. Then cyclic, that should be a cyclic compound. So what I call it PCC. What is PCC? Priyanka Chopra. Okay? P for planar, C for cyclic, then you have conjugated. Conjugated. This you will see. Planar, cyclic, conjugated. So write it down and spam it in the chat box. PCC. Planar, cyclic, conjugated. Okay? Planar, cyclic, conjugated. Everybody in the chat box. PCC is what you have to check. Right? Okay, now what you will see, if PCC is obeyed, then either it will be aromatic or anti-aromatic. If PCC is not obeyed, maybe it's not planar, maybe it's not cyclic, maybe it's not conjugated, right? Any of the condition is not valid, then this whole thing will not be valid. That means it's non-aromatic compound, right? So in aromaticity, what you have, first is PCC you will check. If it is followed, then you will check the electrons, right? If you have 4n plus 2 pi electrons, it is aromatic. 4n pi electrons, it is anti-aromatic. right? That we will see in with the help of examples how to do all of this, right? I'm just telling you the steps of doing that. We are going to apply that just now, right? Now, because basically we are talking about the stabilities here, right? So aromatic, non-aromatic and anti-aromatic, out of this, maximum stability is of aromatic, it's a very stable compound. Non-aromatic is so-so. Anti-aromatic is the most unstable compound. Nobody in this universe wants to be anti-aromatic compound, right? They will not react only. If you say become anti-aromatic, they will not react. They will say, I don't want to become anti-aromatic, I will not form only. Okay? Got it? Yes, everybody? Yes. Okay? Got it? Acha, now we are going to do some questions, right? One by one. Firstly, we will see aromaticity, anti-aromaticity, how it is done with PCC, electrons, everything we are going to do. Okay? Tell me. Ready for the questions, guys? Everybody, Anjali, Kidu, Durga, everyone, Mr. Wolf. What names you guys have, huh? Interesting names. Okay, so let's do the questions now. See, first question is for benzene. Let's see this. Benzene you have. In benzene, tell me one thing. If you have benzene, is it planar? In benzene, this is having what? One hydrogen is here, one hydrogen is here, one hydrogen is here. One to complete the tetravalency. This is the structure of benzene. All of them are sp2 hybridized. It is sp2 hybridized, that means it is planar. It is cyclic also. It is conjugated also. Double bond, single bond, double bond, single bond, double bond, single bond, double, single. Full conjugation it is going on, right? PCC is followed. Now you have to check the electrons. You have to check the pi electrons here. So 1, 2, 3, 4, 5, 6. So you have 6 pi electrons. That is, if you put it in this equation, 4n plus 2 pi. If you put n is equals to 1, that will become 6 only. That means this compound is aromatic compound. And benzene is the most famous aromatic compound. Aromatic means aroma, right? So it's the most famous aromatic compound, right? Okay? Yes. Next, let's see, before going into the next topics, right, more examples, I just want to tell you, here it was very easy to identify whether it's sp2 or not. So, in case of carbocation and carbanion, how you will answer whether it's sp2 or not, okay? So, if it is localized or if it is delocalized, see, if it is localized, that means it is not showing any resonance. In this case, how many sigma you have? 1, 2, 3. 3 sigma, that means it is sp2. Okay. So, localized carbocation is always sp2. If you talk about delocalized carbocation, C double bond C, this is positive, this is CH2, this is H, right? This is delocalized carbocation. How many bonds it is forming here? How many bonds it is forming here? 1, 2, 3 bonds, 3 sigma. If you want to write it here, this will be 3 sigma, okay? So, this will be 3 sigma. So, 3 sigma again means it is sp2. So, in case of carbocation, you don't have to worry about that, right? Because in PCC, when there is complete conjugation, you will always see delocalized only, right? I will show you examples also. In PCC, whether it is under conjugation or it is not under conjugation. So, ma'am, what do you mean by ma'am delocalized? Delocalized means who is not living at his own place. So, sometimes it is moving here. So, now carbocation will move here. So, can you see this carbocation is delocalized, moving here and there, right? Localized, local person. Now tell me, what is a local person? He is local. That means he is living in that area. Delocalized means he don't have a proper space, right? So he is moving here and there and here and there, here and there by resonance. That is why we say delocalized carbocation. Delocalized carbo that is moving here and there is also sp2. Okay, got it? Right. Now let's see this thing. Now let's see, wait a minute. Now let's see carbanion. It is different. This is H, this is H, this is H, this is negative. Now 3 sigma plus 1 negative means total 4. That means it is sp3 hybridized. Then ma'am, what about when it is under conjugation? So let's say this is 2, this is H, this is CH2 negative, right? Now see this very carefully. This will shift here, this bond will shift here, this is because of resonance. This will be CH2, this is single bond C, this is CH2, right? This I have told you in resonance only that it will look like this, right? This I have told you in resonance that how it will be interconvertible in the last lecture. Now see one thing. If you see, ma'am, this is, if you just see this thing, you will say, ma'am, 2 hydrogen, 1, this sigma, 3 sigma, ma'am, 4 means it is sp3. That means planarity will never be followed by carbanion, is it? No, right? Only that negative charge is under hybridization which is localized, okay? This is a localized means this is not shifting. That's why I have added it into the hybridization. But this is a delocalized negative charge that will never be added into the hybridization while calculating the hybridization. So this is having 1 sigma, and here if you draw it like this, this will be I'll just draw it like this only, right? This is first sigma, second sigma, third sigma, so it will be 3 which is sp2. And that's why usually students do this mistake, right? They just see, more knowledge is also dangerous. Sometimes they know that they have to check hybridization, that is sp2, but the mistake that they do is they don't know that this negative is not calculated in delocalization when the negative charge is delocalized. So you will not calculate this when it is delocalized, okay? So in nutshell you can see carbocation or carbanion, if it is delocalized, it will have sp2 hybridization. That means that will be planar, okay? Yes, everybody got it? Now let's do the questions based on this, right? Let's do the questions based on this. In every slide you will see 2 or more compounds. We'll check aromaticity, whether it's aromatic, non-aromatic, anti-aromatic, what is that, right? So if you see this here, this is A and this is B, right? In this case, guys, this is a double bond, so it will be sp2. This is a double bond. Double bond is always sp2. Carbon double bond means sp2. Don't even check it. Carbon double bond means it is sp2. Carbocation, it is under delocalization, is sp2. Carbanion under delocalization is sp2. Double bond, single bond, carbanion. It is under delocalization, under conjugation. So it is also sp2. So definitely PCC is followed here as well. Here as well. It is planar because all of them are sp2. It is cyclic, conjugation is there. Double bond, single bond, positive, positive, single bond, double bond, single bond, positive, complete conjugation. Similarly here, PCC is followed. Electrons are, here you have 2 pi electrons. Here you have 1, 2, and this will also be included. Pi electrons, those are included which are a part of delocalization, because when you shift it here, this delocalization will take place. So that means this negative charge also you will add here. So here you have 4 pi electrons, that corresponds to 4n pi, that corresponds to anti-aromatic, which is very unstable, right? And here 2 pi means which corresponds to 4n plus 2 pi. If you put n 0, it will become 2 pi. So this is aromatic. This is aromatic. So in this case, we can also compare that A is more stable as compared to B, right? Okay, A is more stable as compared to B because that is anti-aromatic, this is aromatic, right? Okay, yes everybody, okay. Next is, if you see this compound here, right? If you see this compound here, double bond means sp2, 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 sp2. Carbon ion delocalization means sp2, 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 all are sp2. That means it is planar. I just told you, see, either you calculate everywhere or you just know one thing, that carbocation or carbon ion under delocalization is sp2, right? You don't need to think about planarity again and again. So here planar it is, cyclic it is, complete conjugation is there. Planar it is, cyclic it is, negative single bond, double bond, complete conjugation is there. Here also complete conjugation is there, PCC is followed in all the cases. Now electrons are 2 electrons here, so 2 pi electrons. Here 1, 2, 3, 4, 5, 6, 6 pi electrons, right? Here 1, 2, 3, 4, 4 pi electrons. 4 pi electrons correspond to anti-aromatic, that means 4n plus 2 pi. This corresponds to 4n plus 2 pi. That means if you put n1, then it will become 6 electrons, so it will be aromatic. I'll just write it here, this will be anti-aromatic, right? And this is 2 electrons, again it is corresponding to 4n plus 2 pi. Because if you put n is equals to 0, that will become 2 pi electrons. So this is again aromatic. So these two are aromatic, this one is anti-aromatic in nature. Okay, got it? Yes everybody? Yes. Okay, here you can't tell the stability like that, but you can tell that these two are aromatic, right? Compare these two. Let's see. PCC is followed double bond. See, it is also sp2, 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 sp2. PCC is followed. It is cyclic, conjugated, conjugated. So PCC is followed in both the cases. Here you have 1, 2, 3, 4 pi electrons. Here you have 1, 2, 3, 4, 5, 6. 6 pi electrons, right? 1, 2, 3, 4, 5, 6. 6 pi electrons. Negative charge holds 2 pi electrons, right? So that's why here what you will have, this is 4n pi electrons. That is, it is anti-aromatic, right? This will be 4n plus 2 pi electrons. That is going to be aromatic. So definitely this will be more stable if they ask you the stability. Otherwise you should know that this is anti-aromatic, this is aromatic. Okay, right? Okay. Understood everybody? Which B? This one? This one? See, electrons 1, 2, 3, 4, 5, 6. That's why 6 pi electrons which correspond to the set of 4n plus 2 pi. Okay? Yes. Understood? Yes. A is anti-aromatic, B is aromatic, and that's how you have the answer. Next question is this one. Let's see this. These are all your PYQs. All your PYQs only that they have asked you, right? So if you see sp2, 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 sp2. Why? Because either it's double bond or it's carbon ion, carbocation, right? Now, cyclic complete conjugation, cyclic complete conjugation. So PCC is followed here also, PCC is followed here also. Here you have 1, 2, 3, 4, 5, 6 pi electrons. Here you have 1, 2, 3, 4, 5, 6, 7, 8 pi electrons, right? 6 pi electrons corresponds to 4n plus 2 pi. If you put n is equals to 1, it will become this. So it is aromatic, right? This corresponds to 4n pi electrons. If you put n2, this will become 8, right? That means this is anti-aromatic. So answer is A is more stable as compared to B. A is aromatic, B is anti-aromatic. Very good, Rama, very good. Right? A is aromatic, B is anti. Can you explain how the formula works? Okay, you just have to put the values. This is 4n pi. Now that means if n is 1, it will be 4. If n is 2, it will be 8. If n is 3, it will be 12. If n is 4, it will be 16. So these are the electrons and so on. You put n value increases, 4n pi will increase. If you have 4n plus 2, that means if you put n1, that is 6. n0 means 2, n1 means 6, n2 means 4, 2, 8, 9, 10. Okay, simple, that way it will work, right? Okay, clear everybody, clear Durga, how it works? Yes. Which part you are not able to understand, Geeta? Let me know which part. Which part you are not able to understand? Formula part or PCC part, which part? PCC, planar cyclic conjugated, you will check. Planarity means sp2 hybridized you should have. Double bond carbons are always sp2 hybridized. Carbocation I told you in delocalization is hybridized, sp2. Right? Carbanion also in delocalization it is sp2 hybridized. Right? So PCC, this is how it is followed. Right? If it is PCC, check the electrons. 6 pi electrons falls to this category, this falls to this category, this explains anti-aromatic, this explains aromatic, right? Okay. Yes. Right? Okay. Yes. So now let's see, now it is going to get even more interesting now, because now you will have the other atoms like nitrogen, oxygen in between, which has lone pairs. Now see some very important facts I am going to tell you. So please listen carefully, right? Please listen carefully. You guys don't just be too lost in your own thoughts. Please listen carefully, right? And don't look at chats, right? For some time, for next 2-3 minutes, don't look at charts, because very important point I am going to tell you here, right? See, first thing is this nitrogen always have one lone pair, right? Carbon with double bond is sp2, that I have already told you. But what about this nitrogen? Ma'am, 1 sigma, 2 sigma, 3 sigma, lone pair. Ma'am, it is 4. It should be sp3, isn't it? Isn't it? No. The lone pairs that are involved in delocalization are not a part of hybridization. If you see the delocalization is with this lone pair shifts here, this pi bond shifts here. That means this lone pair is involved in the delocalization. Lone pair that is involved in the delocalization, I have also written here, while calculating hybridization, lone pair involved in delocalization is not involved. In calculating hybridization, lone pair involved in the delocalization is not calculated in hybridization. So this lone pair is not a part of hybridization. You have 3 sigma bonds, so this is sp2 hybridized. If you see this here, out of these 2 lone pairs, only one will be a part of delocalization. So this will shift here, this will shift here. That means this is a part of delocalization. This lone pair is a part of delocalization, so we will not calculate it in hybridization. Hybridization will be 2 sigma plus 1 lone pair, which is 3, that means it is sp2. Here it is, you have 3 sigma, that means it is sp2. Tell me, is that clear why this is sp2 and why nitrogen is sp2? Right? That is clear, guys. That is clear. It's a very important thing, right? You should know why planarity is there. Then we can see it is cyclic. We can see the conjugation is there, right? So I'll just copy paste this thing. Now you should calculate. See why it is cyclic, because it is cyclic. This is cyclic. So PCC is followed. Conjugation means lone pair, single bond, double bond, double bond, single bond, double bond, double bond, single bond, lone pair. So complete conjugation. Similarly here. So PCC is followed in both the cases. Right? Now, next is to calculate the pi electrons. While calculating pi electrons, lone pair in delocalization are involved. Lone pair not in delocalization are not involved, right? So this is a part of delocalization. So this will become 1, 2, 3, 4, 5, 6. So this will have 6 pi electrons. This is a part of hybridization. This lone pair not showing delocalization. So here you will have 1, 2, 3, 4, 5, 6. So it will be 6 pi electrons, right? Both of them we can see are aromatic. This is 4n plus 2 pi, that means it is aromatic. This is also aromatic. Right, everybody? Okay. See what I told you here. Lone pair, that is not out of these two lone pairs, only one will be involved in delocalization, right? So the lone pair that is involved in delocalization is not a part of hybridization, right? So that's why this lone pair is involved in the hybridization. So 2 sigma plus 1 lone pair is 3 sp2. That's how we define that why nitrogen and oxygen is sp2 in this case, right? And here, while calculating pi bonds, only those lone pairs are added which are a part of delocalization. This is showing delocalization, this is showing delocalization. So these two electrons are added. So it is 2, 3, 3, 4, 5, 6, 2, 3, 4, 5, 6. Right? Okay. Right, everybody? Yes. Now, let's see this. Let's see this one. Let's see this one. Let's see if you're able to answer this or not. See, boron is actually electron deficient. It is having electron deficiency because its octet is not complete, right? That's why this pi electron will shift here, this pi electron will shift here, right? So conjugation is there. Double bond, single bond, vacant. Double bond, single bond, vacant. Double bond, single bond, double bond. So complete conjugation is there. It is cyclic, yes. What about planarity? This is 1 sigma, 2 sigma, 3 sigma. That means it is planar also. 3 means sp2. This nitrogen, if you see here, this nitrogen here is involved in the delocalization, right? So complete conjugation is there. It is cyclic. Planarity, if you see, this lone pair that is involved in the delocalization is not a part of hybridization, right? So hybridization is defined by this sigma, this sigma, this sigma. That means 3 sigma is sp2, right? So it is also planar. It is also planar, right? It is also planar. Now this nitrogen also has a lone pair, but this is not in hybridization or delocalization, right? This is neither a part of hybridization nor a part of delocalization. It is not showing, this is a part of hybridization, wait a minute, this not in delocalization. It is not a part of delocalization. So if you see this here, it is connected to 2 sigma and 1 lone pair. So this nitrogen is having 2 sigma plus 1 lone pair, that's why it is 3, that's why it is sp2. Okay, I am explaining you everything here, right? This much detail, though no one will tell you that why this is sp2, why this is sp2, everything I am explaining so that you understand things in like real, that why planarity is so important. Planarity is important, that's why chemical bonding I have taught you before this, right? So we can say carbon with double bond is planar only. So planarity is there, right? Now calculate the pi electrons. Here you have 1, 2, 3, 4. 4 pi electrons. Boron is electron deficient only. Here you have 1, 2, 3, 4 and these 2 electrons which are involved in delocalization. So it is 6 pi electrons, which means it is aromatic in nature. 4 pi electrons means this is anti-aromatic in nature. This is showing 4n pi electrons. This is 4n plus 2 pi electrons. Okay, got it? Right? Yes, everybody? Yes, everybody? See beta, what I told you, firstly you have to see the hybridization, right? For hybridization, two simple concept I am repeating again and again. One is that the lone pair that is in the delocalization is not a part of hybridization. So this lone pair will show conjugation here. We have studied resonance. So that's why 3 sigma means sp2. This is not a part of delocalization because it is not involved in delocalization. Just remember one thing. When nitrogen is having lone pairs here, this lone pair is a part of delocalization. When you have a double bond next to it, let's say here you have a double bond, here you have a double bond, it is part of delocalization, right? When it is connected to 3 sigma bond and after that you will have a double bond. If nitrogen, directly to the nitrogen you have a double bond, then this lone pair is not in delocalization. In delocalization. This is not a part of delocalization, right? This will not show any delocalization. So that's why when you calculate this, this is 1 sigma, 2 sigma, 3 sigma, 3 sigma means this is sp2. When you calculate this one here, this is 1 sigma, 2 sigma, 1 lone pair. 2 sigma plus 1 lone pair is 3, that is sp2. Okay? This is what I was telling you, that this is sp2, this is sp2. Calculation of pi, the lone pairs that are involved in delocalization, this is involved in delocalization. So 1, 2, 3, 4, 5, 6. Okay? Right? Yes? Understood? Okay. So let's see if you can understand, if you can answer this or not. Let's see if you can answer this or not. Got it, ma'am? Very good. My throat is literally blocking at this point. This is your pyridine, right? Pyridine, see, nitrogen will, if your basics are not clear, like nitrogen, ma'am, why you have a lone pair here, then I can't do anything, right? Because that is a part of chemical bonding. That is very basic thing, right? That's why I taught you chemical bonding before GOC. I could have taught you GOC, right? But why chemical bonding before that? Because these things I have explained you there. That nitrogen will have one lone pair if 3 bonds are connected, right? Will this nitrogen be a part of delocalization or not? Let me see who will answer this. Will this nitrogen be a part of delocalization? After this we are going to start annulenes. Yes, everybody? will this lone pair be a part of delocalization or not? If you answer this, that means concept is clear, right? That means concept is clear. No? Okay, very good. Yes. It is not a part of delocalization. Delocalization is whenever you have nitrogen double bond is connected. I have told you the short trick also. When nitrogen double bond is connected, it is not a part of delocalization, right? Shortcut also I told you, but with logic also you should know that these double bond, single bond, double bond, single bond will be delocalized, right? So that's why this will be sigma, sigma and lone pair. So nitrogen is having 2 sigma plus 1 lone pair. That's why it is 3. It is sp2. This lone pair here, it is a part of delocalization. How? Here, the movement here, right? It is a part of delocalization, right? So it is a part of delocalization. So you will say this particular nitrogen, it will have 3 sigma, right? Nitrogen is having 3 sigma, so that's why it is sp2, right? Now, because this is a part of delocalization, so what you will do while calculating the number of pi electrons, PCC is followed. This is sp2, so it is planar cyclic conjugated, it is planar cyclic conjugated sp2 that we have seen, right? This we know, carbon ion under delocalization is sp2, that we have done. Now what about the pi electrons, right? That is involved under delocalization. So it is 1, 2, 3, 4, 5, 6. So it is 6 pi electrons, right? Here you have 1, 2, 3, 4, 5, 6, 7, 8. 8 pi electrons. So 8 pi electrons means it will be 4n pi. That means it is anti-aromatic, right? 1, 2, 3, 4, 5, 6, 7, 8. Right? That's how you have 8. Right? Yes. This is 6. So that will be aromatic in nature. Got it? Tell me if that is clear to all of you or not. Tell me guys if that is clear to all of you or not. Right? Okay. Let's move to the last part of today's lecture, that is annulenes, that is based on aromaticity. Okay? Yes, everybody? Okay. Oh, no issues. Right? Why ma'am sp2? Array sp2 it is... This lone pair is involved in delocalization. Fourth or fifth time I am repeating this. Lone pair involved in delocalization is not a part of hybridization. So it is 3 sigma, so sp2. This lone pair is a part of delocalization. Is not a part of delocalization because it is already delocalized here. I have also told you the trick here, right? How to do that. Okay, sure. Now let's see annulenes, right? Let's see annulenes. Annulenes are monocyclic, only one cycle is there. Full conjugation of double bond, single bond, double bond, single bond is there. Alternate double, single bond is there, right? So it is monocyclic compounds showing complete conjugation by double bond, single bond, right? And the number that is mentioned here is defining the number of carbons or the number of pi electrons, right? Because if you see, number of carbons are 1, 2, 3, 4. Number of pi electrons are 1, 2, 3, 4, right? So this is actually mentioning number of carbons, or directly you can say number of pi electrons. Okay. So if you see this here, right, firstly in annulenes if you see double bond, all are sp2, planar, cyclic. Complete conjugation is a part of cyclic, and complete conjugation is a part of annuline. So CC will always be followed. You just have to check planarity. What I am saying, you just have to check the planarity. Cyclic complete conjugation is in its definition. So you don't need to see it again and again. Okay, so just check the planarity. Planarity is there, it is sp2, 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 sp2. Okay, 4 pi electrons it has, so it will be anti-aromatic. It will be anti-aromatic. Okay, yes. Okay, let's see the next one. Let's see the next one. This is benzene only. So it is how many carbons, how many pi electrons you have? 6 pi electrons. PCC is followed here. 6 pi electrons means it is aromatic in nature. Right? This means it is anti-aromatic in nature. Right? Let's see this one. 8 annuline. Very important. Mark it important. It is cyclic. It is conjugated, but not planar. It is not planar. You will say, ma'am, why it is not planar, ma'am? This is sp2, ma'am. This is sp2, ma'am. This is sp2. This is sp2, 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 sp2. Ma'am, even then it is not planar? Yes. Why? Because it has a tub-like structure. It has a structure like this. Okay, that's why you have to remember this. Okay, that's why this question is asked. Okay, it has a tub-like structure like this. Okay, which is definitely non-planar. And guys, whenever something is non-planar, whenever PCC is not followed, it automatically becomes non-aromatic. Okay, it automatically becomes, yes, it has tub-like structure, that's why it is anti-aromatic, it is non-aromatic in nature. Right? Okay, it is the exception. Right? So mark it, no. Okay? So mark it very, very important. Very, very important. If they ask you annuline, definitely they will ask you this. And this is your PYQ only. Right? This is one of the PYQs. They have asked you this already. Right? If you see this, 10 annuline, just tell me one thing, 8, 10 and 12, these are non-aromatic. Just remember, 8, 10 and 12 are non-aromatic. I'll tell you why this is not aromatic. Right? Here, cyclic and conjugated is always followed. Planarity is not followed. Here also, planarity was not followed, right? So if planarity is not followed, why so, ma'am? See, here this carbon is sp2, this carbon is sp2. sp2 carbon means it should have a trigonal planar structure like that. It should have a trigonal planar structure like that, which should have 120 degree angle. Okay, 120 degree angle, right? Now that means this hydrogen should be here. This other hydrogen should be here. This is actually on the planar side. So firstly I will draw simple this only, right? Now these two hydrogens, right? Because of the repulsions, they create angle strain. Right, because the size is small of this compound, the difference is not that much, right? They are very closer to each other. And some students, they say, ma'am, it can be here, ma'am, it can be here. This is what I am telling you. Because they are like, this is hydrogen, they are causing repulsion. So what will happen, I'll just show you that. This hydrogen and this hydrogen, they are causing repulsion. That's why what will happen? One will move this side, one will move this side. So they will be now non-planar, like this they will move, right? They will be non-planar now. They will move out of that 120 degree angle, right? Yes, right? So earlier they used to be like this, right? But they were repelling each other, so they went non-planar, right? The angle shifted, right? So that's why one hydrogen here, other hydrogen here, and it is not on the same plane, it is outwards. This is slightly outwards here, that is slightly outwards here. It's like this. Earlier they were like this, now it's like this kind of situation, right? So that is why it is non-planar, that is why it's non-planar, and that is the reason it is non-aromatic. So you don't even have to calculate the number of electrons directly, because PCC is not followed, so directly we can say it is non-planar, non-aromatic. Similarly, you have with 12 annuline. Right now, this is an experimental data. How will ma'am we get to know whether repulsion? This scientists have already discovered that in this case repulsions were there. In 14 repulsions were not there. In 10 and 12 repulsions were there. Angle was drifting, right? So here also this should be here, this should be here, this should be here. Again they showed angle repulsion, and because of angle strain that became non-planar, that is non-aromatic, non-aromatic, right? That became non-aromatic, right everybody, right? Okay, PCC, out of PCC which is not followed, planarity is not followed. So even one of them, if it is not followed, it will become non-aromatic, right? Then 14 annuline, here the compounds will be slightly away from each other, right? They will be, this H will be away from each other. So no repulsions between these hydrogen were observed. So now we'll see that 14 pi electrons means how much? If you see 4n plus 2 pi, if you put n is equals to 3, this will become 4 into 3 plus 2, that is nothing but 14, isn't it? That means it is a concept of aromatic. That means this one is aromatic in nature. Okay, that means this one is aromatic in nature. 16 annuline. If you want to calculate, you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Right? That's what I am telling you. You don't need to calculate the pi electrons here. Okay? But if structure is given to you, then definitely you will have to calculate, right? So 16 annuline, again hydrogens were very much away from each other. The structure I have drawn small, but it is very, very away from each other, right? Okay? So 16 pi electrons corresponds to 4n pi. If you put n is equals to 4, then this will become 16 pi. So that means this is a concept of anti-aromatic compound. Anti-aromatic compound. Okay? Got it everybody? Last is 18 annuline, right? This kind of structure. So you have H here, you have H here, you have H here, you have H here, here and here. No repulsions will be there. So 18 annuline, 18 pi electrons. This corresponds to 4n plus 2 pi. If you put n is equals to 4 here, this is 4 into 4, 16 plus 2, 18. So that means this is a concept of aromatic. Okay, tell me. Just remember, I'll tell you a simple thing to remember this, right? Okay? Bridged compounds, you're talking about that in the bridge when you have sp2 hybridization, right? That you're talking about. That we'll not talk about now. Okay, we'll talk about later, right? Now, if you see this now, just a simple trick here we have. Simple trick is, not even trick, it is like simple, you should know this, just in the end, just remember this table. Annulenes 8, 10 and 12 are non-planar. That's why they are non-aromatic, that's it. Others you just see, which one is showing you 4n pi and which one is showing you 4n plus 2 pi. According to that, it will be aromatic or non-aromatic. Like 4n plus 2 pi electrons, it is shown by 6, it is shown by 14, it is shown by 18, right? Yes. So 6, 14 and 18 is aromatic. 4 and 16 is anti-aromatic, right? And that's how you know this, right? Okay. Okay. Yes, everybody. Let me know if that is clear, right? Okay. Now the last part I am going to do some questions based on aromaticity. Let's see that, okay? Let's see that, guys. Let's see that. I have 4% charging. I have 0% charging. Don't worry, in 4% charging, we'll make it. We'll make it. We'll do that, right? See, last part, actually not 4% charging. We need like 7-8% charging we need. See one thing, this one is more electronegative, so I'll shift the bond here, and what you will have here is this kind of structure. This is CO negative, this will be positive, and here it will be C, this will be O negative, this will be positive, right? Just focus on this particular thing, this thing. Just focus on this thing, right? Just focus on this thing. So if you see this here, this is PCC is followed, right? 4 pi electrons it has. That means this is anti-aromatic, right? If you see this, in this case, this is PCC is followed and this is 2 pi electrons. So this is aromatic in nature, right? So if they ask you a question like that which is aromatic, which is anti-aromatic, this is how you will tell, right? Because the pi electrons will be shifted towards more electron negative, right? If you have a compound like this, right? Here carbon is more electronegative, that means this will shift here, this will shift here. So we can draw it like this. Same compound, but everything will change. Okay. Now if you see, this is how many electrons? 6 pi electrons. 1, 2, 3, 4, 5, 6. That means it is aromatic. This is 1, 2, 3, 4, 4 pi electrons. That means this is anti-aromatic. Can you see how based on what is connected to that ring, everything has changed? Okay? Right? Everything has changed based on what is connected to it. Now see this thing. They are asking you that you have this or this. Which reaction, this is sigma, this is pi bond. Pi bond will be shifted on this direction or on this direction, that you have to tell. Okay? So how we will tell that? We'll see both the cases what will happen. Let's say in A case, with A what is happening? It is shifting here, so it will be 1. What I'll do, this will be 1, 2, this is double bond. It is shifting here. So I'll make a negative here because it is shifting here. This will become positive here. Because in A, this has shifted above. It has shifted above, right? So this will be negative, this will be positive, right? Now see what you have here is, now you divide it into two parts, this part and this part, and see the aromaticity. This is 6 pi electrons, that means this is aromatic. This is 2 pi electrons, that means this is also aromatic. That means this shifting is giving you two aromatic things only, so that means it is possible, right? Now let's see in B what will happen. This bond is shifting here. So what we will do, this is 1, 2, double bond, this is single bond, right? This has shifted here, means here you will have negative, here you will have positive, right? Now see this, take these two differently, right? Let's see if you can answer that or not. This is having 4 pi electrons, that means it is anti-aromatic. This is having 1, 2, 3, 4. Again 4 pi electrons. That means this is also anti-aromatic. So definitely A is preferred over B, right? A path is preferred. The shift of A is this way, it is preferred because it is giving you aromatic things, not anti-aromatic. Okay, clear everybody? Very good guys, because of aromaticity, right? So this is how your brain should work. Now I'll tell you how PYQs are asked, right? And you will see latest PYQs are simple than what I have told you. Okay? Whatever I have taught you, right? It is more than sufficient, right? Because PYQs now you will find is very simple, right? So correct order of stability they are asking you for carbocation, right? Now bacha, before going into this, next lecture is going to be based on stability only, right? So remember that we are going to tell you about the stability based on BARHI. In next class, we'll talk about more and more compounds, exceptions also, everything we'll talk about. But here B for back bonding, A for aromaticity, resonance and hyperconjugation, then inductive. That means firstly, if back bonding, can you see anywhere? No, right? Back bonding we can't see anywhere. Aromaticity I can see, this is 1, 2, 3, 4, 5, 6 pi electrons, so this is aromatic. And aromatic compound is highly stable, so we can say that C is very stable. After that, because of resonance, here this resonance and this resonance, 3 resonances you have. Because after aromaticity you have resonance, so you have 3 resonances here, and here you have 1, 2 resonance. Resonance between this thing. This is showing resonance, right? We have studied it. In the last class, we have studied it, that how this will show resonance, right? So PH phenyl to phenyl group, when carbocation is directly attached, it will show resonance, right? So this is showing 3, this is showing this, so it will be A and then it will be B. This is only showing you plus I effect, inductive, and this is also showing you plus I. Can you see, not even plus I, firstly we'll see hyperconjugation here. Hyperconjugation is, this is alpha, actually not inductive, we'll see hyperconjugation, because hyperconjugation, this also we'll talk about. In most of the cases, hyperconjugation and inductive will give you the same order, but in some cases, hyperconjugation gives you a different order. In that case, answer will change. That's why hyperconjugation I am talking about. This is alpha, this is 3 plus 2, that is 5 alpha, right? It is showing hyperconjugation, but hyperconjugation is least prioritized here. So that is why answer will be CABD is the correct answer here. So answer will be CABD, that is D is the correct answer. Okay. Next question, if you see 2025 questions these are. Consider the following, this is a compound that is given to you. They are saying most stable and least stable carbon radicals, respectively produced by homolytic. Homolytic means, for example, homolytic cleavage of corresponding CH bond. Okay. Homolytic cleavage means this is CH bond, this and this, that means this will form C free radical, this will form H free radical. Okay, that is homolytic cleavage. Heterolytic cleavage means where more electronegative will take both the electrons, like this. This is heterolytic. Okay. Now we'll talk about this. If here you have homolytic cleavage, this will give you C free radical, right? If you see this here, this is based on hyperconjugation. If you see this here, if this gives you C free radical, then this will be alpha, this will be alpha. This free radical is not stable because on multiple bond you have free radical, so this is eliminated. If on second you have this free radical, this is alpha and this is also alpha. This alpha has 1 hydrogen, so here you will have 1 alpha hydrogen. right? One hyperconjugating structure. If this is free radical, then this is alpha, this is alpha, this is alpha. That means 3, 4, 5, 6, 7, 8. 8 alpha it will give you, right? 8 hyperconjugating structure. If this CH bond you will break, then this is the free radical. In that case, this is alpha. Again, it is 1 alpha hydrogen. Okay. If this CH, so they have not even given, right? This CH is least stable. They are asking you, most stable will be third, least stable will be 1. This one will be the least stable. So third and 1, 3, 1, 3, 1, 3, 1. Do we have that? 3, 1, we don't have that, is it? Third should be most stable. If this CH bond breaks, this is alpha, this is alpha, this is alpha, 3, 4, 5, 6, 7, 8. So third should be the most stable, right? So I think answer should be A. Na? Why? Wait a minute. Second is most stable due to resonance stabilize. Oh, shit. We have forgot resonance only. I was just checking hyperconjugation. That's why the answer is coming out to be wrong. Yes, that's why the answer is coming out to be wrong, because we have to check Barhi here, isn't it? We have ignored, back bonding is not there, aromaticity is not there, but resonance is there. If this is the free radical, multiple bond and free radical will give you resonance here. So resonance is more stable, right? Definitely yes. So that means second is more stable. Yes, that is true, that second is more stable because of resonance, and first is least stable because what we have is on a multiple bond free radical or carbocation is not stable, right? So this is least stable, right? Okay, yes, understood? Okay, so answer will be second is more stable based on resonance. That's why, you know, this factor is very important, that you have to apply this factor. Back bond is not there, aromaticity is not there, then I'll look for resonance, right? Then I'll say that this is, because no matter this has 8 alpha hydrogen, but this is showing you resonance. This structure will show you resonance. So that's why second will be most stable and first will be least stable. So answer will be D is the correct answer. Okay? Yes. This is very simple. Correct order of stability of carbanion, right? So it is exactly based on aromaticity, right? So if you see this here you have 4 pi electrons, right? Here you have, this is non-planar, non-aromatic. This is also non-aromatic. This is 1, 2, 3, 4, 5, 6, 6 pi electrons. So D will be aromatic. This is anti-aromatic. So D will be maximum stable and A will be least stable. That is only here, right? That is over here, right? Okay. Then if you want to calculate from here, that is not based on resonance or aromaticity. That is simply based on that pentane ring, that is cyclopentane ring is more stable as compared to butane ring. So C is more stable as compared to B, right? Okay, got it? So based on that, you will have A as the correct answer, and that's it. Now I'm giving you one homework here. That is again a JEE question, JEE 2025 question, that is based on, and wait a minute, here you will have a negative charge, here you will have a negative charge. Yes. So correct order of stability you need to tell, and I am not going to give you any hint, you need to tell yourself all these compounds we have seen in today's lecture. All these compounds, right, we have done in today's session, right? Okay everybody. Most welcome, Rama Raju. Now I'm waiting for you guys to answer it in the comment section. Your answer, take the screenshot here and write the answer in the comment section, right? Okay. So I'm waiting for your answer. Let's see how many of you put some efforts, right? Let's see that. Right, and before going, again I am reminding you that MB SAT scholarship program registration is free of cost, guys, and the rewards are like awesome, right? So you will get up to like 100% scholarship, like on all the Vedantu courses. You will get iPhone, iPads, cash rewards you will get, right? All the things, right? Worth 2 crores, right? And 150 crore worth of scholarship you will get, right? But what you need to do, you need to give this test 4th, 5th, 11th and 12th, any of the dates, right? And Saturday, Sunday only it is, so it will be like easy for you. Nearest Vedantu center you will visit and give this test, right? And guys, here, if you're among 2.5 lakh students, which I think is quite easy, why? Because you're already preparing for it, right? So what if you get something from there, right? So that's why I'm saying that you're already preparing, you're already studying, no extra thing you have to do. You just have to register and give the test. Right? Take it like a mock test, right? 15 question each, physics, chemistry, math will be asked. Go and give that, right? Let's see what happens, right? Okay, so, okay then, thank you so much, Durga. I understood what you told. Thank you so much. All these comments that you're saying now, write it down in the comment section, because these chats are going to fade away, right? But one thing will not fade away, that is your comments, right? So write everything that you have in the comment section so that I can also see that whenever I feel low, whenever I feel like I don't feel like teaching, I am demotivated, I just go through your comments and I feel like these are the kids for which I am teaching, right? So write it down in the comment section, right? And also do your homework. Right, ma'am, is it free? Yes. Registration is completely free of cost. Nothing, not even a single penny. In fact, you will get rewards only, right? All these things you will get, right, after giving the test, right? Okay? Yes. Joshua, just be on track, do your 100%, make day and night equal and work hard as much as possible, right? So what we can do is we can utilize the time that we have, right? That is in our hands. Thing that has already gone, it's gone, right? What was in your luck, you can't change that, right? But one thing you can change, your hard work, right? So do hard work and just be passionate about what you are dreaming of, right? And yes, just keep moving. Every day compare yourself if you're like learning something new or not. If you think that yes, I'm better than before, right? Yesterday, today I learned something new that I was not able to understand before. That means you're on the right track and that means you can get everything that you want, right? Okay. Ma'am, when you will start Alkenes. After finishing this, I'll start with hydrocarbons, right? Then I'll start Alkenes, right? So, yes. Okay. Okay then guys, I'll see you all in the next class. Bye-bye. Have you finished GOC? No, I have finished just the effects now. After this, I'll do stability of intermediates, acidity, basicity. Then we'll do isomerism in the next week. Then we will move towards hydrocarbons, then haloalkanes, haloarenes. Okay? Yes. Ma'am, in the last date of registration, today itself you need to register yourself, right? You want to wait for the last date, right? Then the slots, weird slots will be given to you, right? Okay, so it's better to register yourself as early as possible, right? Okay, so that your slots are booked, right? Because we only can have limited seats, right? So that's why. Okay? Yes. Okay then guys. Yes, I have just told you that this week we'll do stability of intermediates, acidity, basicity. Next week we are going to do isomerism. Next week hydrocarbon. Next week haloalkenes. Next week alcohol phenols. And like by the end of October we'll finish our organic chemistry. Right? Okay? Yes. Okay then guys, bye bye, take care and I'll see you all in the next class and I'll see how many of you give your homework in the comment section. Till then, bye.